Assalamualaikum and good day everyone. So we will cover the next, which is chapter 5, integrated circuits. Okay, you may see the slides here might have different number with the module. Don't worry, it still cover the same. Okay, so the important thing is that we must fulfill the week. What should be learned on that week? So the next one will be our week 7. Okay, here. So what should be covered is the chapter 5, which is the digital IC, and it is about IC classification, CMOS versus TTL performance characteristics, voltage level, propagation delay, power dissipation, noise margin, fan in and fan out. Okay, the corresponding chapter in the module for this chapter is actually module chapter 16, logic family, page 211 until 228. Okay, so please read from the module for these pages. Okay, and if you guys have any question, feel free to let me know. Okay, so for this week 7 I will use this slide. Okay, characteristic of IC. So what is IC? IC stands for integrated circuits. Okay, characteristic of IC. Okay, now we go first to the packaging. Okay, IC is a group of gate that fabricated on a single chip of silicon. The IC come in different shape according to the packaging, size, operating condition, and cost. Okay, so this one you can see. Okay, some of them should be shown in data sheet. Okay, so I hope maybe you guys can try to find the available chip and you can see the data sheet. You can learn from there. Okay, the important parameters. Okay, now there are three types of packaging. One is dual inline package, which is DIP. What does it mean by this is that you have two parallel row of pin for plug-in mounting. So here you have two parallel rows. Okay, one and you have another one. Okay, this one is not shown. Okay, so you have two. Okay, two parallel row of pin for plug-in mounting. And then the other type of packaging is small outline IC. This is for surface mount design. Okay, and small chord line J-lead COJ use J-shaped lead that curls underneath the package body. So this one require socket to mount. Okay, now moving to the next. So for DIP, dual inline package, the pins are numbered counterclockwise with pin 1 is located close to the notch. Okay, later on when you see an example of chip, okay, you will notice usually they have a notch here. Okay, usually you have a notch, and then it should have marking, because if it doesn't have marking, we don't know whether this one correspond to pin 1 or this one correspond to pin 1. Okay, so if there is marking, this is means that it is a pin 1, and then the numbering should follow counterclockwise. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so this is the example of the DIP chip. Okay, so this is a basic gate. Okay, basic gate in DIP packaging, dual inline packaging, for the 74 times 00 series. Okay, you can see here 74 times 00. You have a 4 NAND gate. Okay, and you see there is a VCC. VCC is actually the supply voltage, and GND is actually the ground. Okay, so you need a VCC to turn on the chip. Okay, and depending on type of chip, okay, sometimes they requires plus minus 5 volt to enable it. Okay, to turn it on, and some chip may require can withstand more range of voltage. Okay, but normally for electronics it's usually within 5 volts. Okay, but it's not all electronic limited to this voltage. Okay, you will learn later on in this subsequent presentations. Okay, so characteristic of IC classification. So IC can be classified into 4 groups. Okay, we have small scale integrated circuits, SSI, medium scale integration circuit, MSI, large scale integration circuit, LSI, and very large scale integration circuit, VLSI. Okay, so what is SSI? Okay, SSI is a small scale integration circuit. Okay, it's small, and normally it is not much used today. Okay, we don't really use it today. And medium scale integration content, okay, for example, a multiplexer, decoder, or register. Okay, for the large scale integration circuit of LSI, okay, sometimes it have a small, can be small microprocessor, programmable logic device, and small memories. Okay, VLSI is a microprocessor. Okay, so the complexity, if you can see range of complexity, so this one is the easiest, and of course this one will be the complicated one. So the acronym is this. When we talk about VLSI, you should know that this actually refers to VLSI. Okay, so numbers of gates in the small scale integration is less than 10, and then this is the corresponding number. Okay, you can actually refer. That's why you see SSI is not really much used. It's just contain very small gates. Okay, example, individual gates. For medium scale integration, flip-flop registers. Large scale integration, example, memories. And very large scale, like I told just now, is a microprocessor. Okay, logic family is a collection of different ICs. Okay, logic family that have similar characteristics. IC can also be characterized by the fundamental technology that is being used. Okay, so you should know there is two common technology that usually use. Okay, we usually use TTL and CMOS, and also by CMOS. Okay, this one is a combinations. Okay, so what is TTL? Is a transistor logic. So use bipolar junction transistor. So you guys know, right, from your school, when you have a transistor, is actually this one, right? Okay, where you have your where you have this label here and here, right? Later on, okay, I think you guys know this already. This is example of transistor. Okay, this is a transistor logic where it used bipolar junction transistor. CMOS stands for complementary metal oxide semiconductor. This one using the field effect transistors. BiCMOS is combination of both TTL and CMOS. Okay, the logic family can be characterized according to these parameters. Okay, you see first is supply voltage, because different technologies have different voltage that able to be tolerated. Okay, and some of them they may require only 5 volt, and some of them they can be used with much higher range of voltage, means not limited to 5 volt. It can be 15 volt, 10 volt, 18 volt, for example. Okay, and then the other parameter of differentiation is the logic level. The next is power dissipation. This is propagation delay. Propagation delay is for example, the difference between when you have an input signal. Okay, it will not be directly we will not directly obtain the output. Okay, there will be some delay because it's going to pass through the chip. Okay, so there is propagation delay. If this one we need to consider. Okay, in designing circuits. Okay, next is a noise margin. Noise margin is the noise, okay, that is exists between the voltage level. Okay, for example, it can disturb the let's say we take this 2 volt as the to be accepted as logic 0. However, if the noise is higher, maybe our 0 volt, maybe our 2 volt can be 2.1, means increase. Okay, increase by, but in the first place it should be 2 volt and below to be accepted as a logic 0. So this is what we considered in the noise margin. Okay, next is a fan out. Fan out is a loading. Okay, means that how much output can be connected to how much chip can be connected to a single output of that chip. For example, if you have just for example, if you have one chip, one gate here, okay, how many numbers, how many loading you can have, okay, for a single input here connect to single output here, connect to how many load you can add, because this, you know, this one is all having loads. Okay, So how many loading it can able to support, okay, from a single output here, okay, because you see this we will have different current, okay, so the current will be distributed, okay. So we need to consider how much loading it can support from a single output, for example, okay. Now IC parameters, we go to the next one. The first one is the DC supply voltage, okay. All digital IC at least has 2 pins, okay, that connected to power rail. So in your chip, okay, in your chip you should have 2 pin minimum, okay. One is your VCC, is the supply voltage, or VDD, okay, and you have ground for sure, okay. Any electronic circuit you should have a supply voltage, and also you should have a ground, okay. So for TTL, the positive supply voltage is VCC and CMOS is VDD, and for negative supply voltage for TTL is ground or VEE, okay. So doesn't necessarily ground, it can be VEE, and for the CMOS negative supply voltage is VSS, okay. So please do understand is that this one VCC, and let's say this is VEE, okay, it doesn't mean that this one must be 1 and this one must be 0, okay. So it can be like you mentioned here positive and negative supply, so it means that this one should be lower than this one, that's all, okay. However, it must be the value must be sufficient in order to make this chip functional, okay. So for TTL, VCC is 5 volt plus minus 0.5 volt, okay. So this is your VCC. So you see there is a tolerance of positive minus 0.5 for the value of VCC. So your VCC can be 4.5 minimum and maximum of 5.5, okay. A TTL gate may be destroyed if the limit is exceeded, okay. So now you realize that actually TTL, okay, it is really the VCC voltage range is really limited and restricted. If you goes beyond that, the gate may be destroyed, okay. For the CMOS case, in contrary, is tolerant to power supply voltage variation. The power supply range from 1.8 volt to 10 volt, 18 volt. You can see it can withstand up to 10 times, okay, because 18 divided by 1.8 you will obtain 10 volt, right? So from minimum as 1.8 volt to positive 18 volt, okay. As voltage is decreased, then so do power consumption, okay. This one is, I think you guys know, right? You can imagine from this equation, okay. If your I is okay, if your IV is decreased, your power is decreased, okay. I think this you can relate, okay. If the voltage is increased, so do the speed, okay. Now IC parameters for the logic level. TTL and CMOS use voltage to represent logic level, okay. Ideally a single voltage value is specified for each logic level, okay. For example, if you have VCC, normally it is logic 1, and if it's ground, it normally is logic 0, okay. But you remember later on, maybe later in the stage you will learn like active low, active high, okay. Now in reality a range of voltage is specified for each logic level, okay. For example, okay, we go for TTL first. For TTL, for the voltage to be accepted as a logic 0, it must be less than 0.8 volt. Means that it can be as high as 0.8, but it can be as low as 0.0, for example, to be accepted, to be regarded as logic 0, okay. And for the logic 1, it must be more than 2 volts, okay. Must be more than 2 volts. Let's say it's until 5 volt, okay. 5 volts. So, and you will have certain region we will regard it as undefined, okay. Undefined. So indeterminate, okay, is the undefined is between 0.8 and 2 volts, okay. This one, the one that I showed just now. How about CMOS? CMOS is logic 0, is considered when it is less than 1/3 VDD. Okay, VDD is your, okay, you see from previous slide, VDD is your positive supply voltage. Okay, and logic 1 is more than 2/3 VDD. Okay, and indeterminate is between half 1/3 of VDD and 2/3 of VDD. So this one, I hope you guys will do some a bit of memorizing. Okay, because it will help you later on. Okay, you need to memorize this characteristic. So this is a further illustration to ease your understanding. Okay, if you see, this is a logic level for the TTL, and this is logic level for CMOS. Okay, let me do for TTL first. Okay, because it's a simplest one. So VCC is between, just now you can see, right, the toleration, the range is 4.5 to 5.5 volts. So this is the maximum. Okay, it can be up to 4.5 to 5.5, and you can see there is VOH and VIH. Okay, so VIH is the minimum voltage level that logic gate will recognize as a logic 1 output. Okay, so it must be as minimum as 2.4 volts. And how about VOH? VOH is minimum voltage level that a logic gate will produce as logic 1 output. Okay, minimum voltage level. Okay, so you have VO and VIH. Okay, then next one is VIL and VOL. VIL is the maximum voltage level that logic gate will recognize as a logic 0 output, and VOL is a maximum level voltage level that logic gate will produce as a logic output. So you can see, right, here you can see is VIL 0.8, 0.4. Okay, this one is the corresponding for the CMOS. Okay, okay, next we go to the next parameter, which is the noise margin. Okay, the noise margin, what is it? The less noise. Okay, you know, noise is actually the unwanted. I think you guys know the definition is from the word itself. We usually don't want noise. Means noise is something that we not want in our system. Okay, so the smaller the noise, the better the system. Okay, so no more noise margin is a measure of the ability of device to reject noise. Okay, means how much the device can tolerate the noise. Okay, so can reject the noise. So if the noise in the circuit is high enough, it can push a logic 0 up or a drop a logic down 1 into the intermediate or illegal regions. Okay, I think this is quite understanding. Okay, understandable. Okay, if the noise is your noise is high, for example, you can only tolerate. Let me get the good example here. 0.8. Okay, let's say it's considered 0. Up to 0.8. Okay, to be considered as logic 0. If the noise is high, okay, for example, this one is to be considered as logic 0. If the noise is high, it can push the logic 0 up, okay, until it cross around the area where we call it not allowed, okay, or undefined. Okay, here. Okay, and if the noise in circuit is high enough, it also can drop a logic down, logic 1, for example this level, which regarded as logic 1, to go down, also to enter the illegal region. So this is the significant effect of the noise margin if it's too significant. Okay, so the noise can come from the electromagnetic disturbance and stray voltage. Okay, what is stray voltage? Stray voltage is the occurrence of electrical potential between two objects, okay, that ideally should not have any voltage difference between them. Okay, so let me see from here. Okay, you see this is your VOH and this is VIH. Okay, this is output and this is input. So maybe you guys are wondering, this one have the same wording, right? So this in the next slide it's explained. Okay, so this is output of here VOH, and this is input VIH, and you have VOL, which is the output low, to be regarded as logic 0, and this corresponding V input low to be considered as a logic 0. Okay, so okay, you see this is the circuit here. Okay, logic level for this gate, and this one is logic level for this gates. Okay, so for example, now you see there is 5 volt and until 2.8 volt to be considered as logic 1 at VOH here. Okay, and however at VIH at the input, okay, it have 5 volt until 2.4 volt to be considered as logic level. So here you can see this is a high level noise margin. Okay, this doesn't mean that the noise margin is high. It means high level because it's a high here, right? Okay, high, which is the logic 1. Okay, high level noise margin. So this is your noise margin. Okay, how about the low level? This is your low level. So 0 until 0.4 volt at output here to be considered as logic 0, and however at the input it is considered from 0 until 0.8 volt to be considered as a logic 0. Okay, so this is the difference, which is the noise margin. So here, okay, you can see the formula. Noise margin for logic high is actually V noise high equals to V output high minus V input high. Noise margin for logic low is V, similarly V and L, V noise low equals to V input low minus V output low. Okay, so please memorize this. It's very simple actually. Okay, not that much to require complicated things to be memorized. Okay, I think it's easy. So because you see VOH is normally high. Okay, and minus VIH. And how about V and L? Okay, V and L, you see it's a V input L here. Okay, minus V or L. Okay, now the next parameters is the propagation delay. Okay, propagation delay, like I told you, is the difference that when maybe your input is at 1 millisecond, for example, but when you expect to get your output, cannot be directly at 1 millisecond, right? Maybe will be some delay. For example, only 2 milliseconds you will receive your output from the chip. So this is the propagation delay. Okay, normally propagation delay, if you let's say if you want to measure from one chip, for example, it is not significant. Okay, but actually propagation delay is very important because let's say in the circuits you have a lot of chip. You need to consider all of these propagation delay from each chip, because if there is a lot of chip and there is a lot of chip in a circuits. Okay, each chip have their own propagation delay. You need to take care of this propagation delay, otherwise your chip will be the design will be out of spec. For example, if you expect from chip 1 to chip 2, you expect the propagation delay around 1 millisecond. But what happened is that your design is improperly, then your propagation delay instead of 1 second, it become 2 seconds. And then in a system where we have a lot of chip, okay, if this 1 delay second is happening, it will create delay to the rest of the chip in the system, to the rest of the gate in the system. So the propagation delay can cause signal to arrive, information to arrive delayed or faster. Okay, so this depends. So and then because every signal have their own logic level, like 0 1 0 1 1 0. If there is delay, the other chip, the next chip will receive wrong information because of the propagation delay. Okay, so we need to control this. This is very important. Okay, so propagation delay is the delay from a change in input to a change on the output. So TPHL, the propagation delay from high to low. Okay, delay from input is given to the time the output changes from high to low. Okay, that's why it's THL. TPLH is actually the propagation delay given to the time from an input is given to the time the output changes from low to high. Okay, so it's a bit the word is a bit not direct and a bit confusing, but it's explainable enough. Okay, so let's say this is your input. Okay, and then after that it passing through the chip or whatever, then you will have a TPLH delay. Okay, you can see the delay. The delay is very important. I mean, the issue of delay is very important. You need to take care, because if this delay happen in one chip and you have the wrong signal going through to the other chips. Okay, so here TPLH is the time taken. Okay, the time taken from the output changes from low to high. Okay, here. Okay, so you can see here we take the intermediate parts, and here is also the intermediate part. You can see the difference. Okay, this is the propagation delay from when its output change from low to high, and this is the delay happen when the output changes from high to low. Okay, here is the value. Okay, this one intermediate I told you just now, right, means it is 50%. Okay, 50% of this we take it here, and also at the output is also the 50% level. Okay, so if it's ideal no propagation delay, which is ridiculous. Okay, normally they have propagation delay. It's just that it is significant or within the spec or whatever. Okay, so if it's good, okay, let's say if ideal chip, okay, then you should have the output. For example, this is your input, right? Your output will be just the same. Okay, your output will be just like this. Okay, they are on the same time frame, but this is impossible because there will be propagation delay for sure. Okay, it's just that is it significant or not significant. We normally want to have low propagation delay, right? Okay, so if the circuit have shorter propagation delay, okay, the circuit will operate faster. So this is logic enough. The next parameters is the power dissipation. Okay, power dissipates when the chip, when we apply the voltage, supplied voltage to make the chip operates. For sure, the chip will dissipate a power. Okay, dissipate a power. So power dissipation of K is the supply voltage multiplied by the supply current. Okay, just like what I showed just now, right? So VCC times ICC. Okay. Remember, this VCC ICC is correspond to which? Correspond to which TTL or CMOS? Okay, you can see it's actually correspond to VCC. So you should know, right? You should know that when we referring to VCC is actually referring to TTL or CMOS. Okay, you guys should able to differentiate by the word. It's by the label, by the terms of the V being used. Okay, for example here VCC times IVCC. Okay, not the current value may not be the same during logic 0 and logic 1. This is understandable. Okay, so when there is chip okay, for example, the current value may not be the same during logic 0 or logic 1. For example, if you have 0 here, logic 0, okay, the current may be different if your output is logic. Let's say this is the same gate, okay, the same chip. Okay, if this is 1, this is 0, the output logic, the value of current may not be the same. Okay, may not be the same. For example, this one is I0. Let's say this one is I1, just to make it differentiate. Okay, the output current I0 and I1 can be the same or can be different. Okay, that's why we need to consider this formula, whereas the ICC is actually ICCL plus ICCH over 2. ICCL is actually the current when the logic is 0, and ICCH is the current when the logic is high. Okay, so ICCL is supply current during low, and ICCH is a supply current during logic high. Okay, supply current. So it's a supply current. Remember this wording is a supply current during logic high and during logic low. Okay, the next last but not least, I think is it the last one? Yes. So the next parameters is the fan in and fan out. Okay, what does it mean by fan in and fan out? So the fan out is a number of standard load that an output can drive. Okay, the fan out is a number of load that an output can drive. An output can only be connected to a limited number of input. Okay, this is very understandable. If you have one chip, you cannot connect it to infinity number of chip. You cannot connect it to 10 number of chip or simply 8 number of chip. You need to consider the fan out. Maybe the chip, okay, maybe the chip, for example, can maybe the chip or the gate can only support up to maybe five chip or 5 gate for at its output. So if you put 6, then it's not working anymore. Okay, because you need to consider the logs. Okay. So an output can only be connected to limited number of inputs before the signal level deteriorates and no longer recognized as a logic 0 or 1. So exceeding the fan out may result in the incorrect circuit operation and may destroy the device. Okay. So you see here, okay, you see here is current when it's output of high, okay, and here is your IH and IH, okay. So input high, okay, input high, output high, input high. So and then this, for example, okay, and then you see 0 and X, okay. This one is a don't care condition, okay. And here is I1 1, and you consider this I output low, okay, I input low and I input low. So the fan out is IOH over IH, comma IOL over IIL. Okay, so you guys can refer also to the module, right, for these things. Okay, let me see for a while for the fan in, fan out, if they provide the example. Okay, so they provide the example, okay, for the TTL, for the main parameters, okay. Okay, so for this operation, you guys can refer to page, okay, for explain on the fan out. You can refer to page 221 of the module until 223, okay. But like I told you guys, you need to read all of the chapter, okay. So for example, for a standard the TTL, the main parameter is that VIH equals to 2 volts. So your IH is 40 microampere. Okay, so we go to the next slide. Okay, okay, for example, VIH is 2 volts, so your IH, okay, I just use the same, okay, I just put the value, okay. This one is for TTL, okay, TTL, for example, your IH is 40 microampere, okay, and your IIL is negative 1.6, okay, milli. How about IOH? IOH is 400 micro, okay, and IOL equals to negative 16 milli, okay. So now let's say we want to see the fan out, okay, we want to see the fan out. I just use abbreviation, okay, because I don't have much space, but I hope it's understand. FO is fan out during logic high, okay. What is the fan out during logic high? So you can just use the equation IOH over IH, okay. So where is IOH? You have IOH here and you have IIH. Okay. So 400 microampere divided by 40 microampere means equals to 10 gates. Okay. Means fan out during logic high only can support up to 10 gates. How about fan out during logic low? During logic low, so it is the equation is IOL over IIM. Okay, so what is IOL? IOL is 16 milli and IIL is 1.6, so it's equivalent to 10 gates. So fan out the able to be supported during logic low is only 10 gates. Okay, so please read the module for more information. Okay, now fan out is much higher for CMOS device than for TTL device. Okay, mean CMOS can support more loading. Okay, IL and IH are extremely small for CMOS. Okay, 1 microampere. In contrast with TTL just now, milliampere. Okay, so you can see this. You can see CMOS they used a very little current. Okay, for IL and IH. Okay, calculating fan out as we did for TTL might yield fan out of 4,000 for CMOS. Okay, compared to 10 for standard TTL. Okay. However, increased fan out result in increased delay due to input capacitance. Okay, this is normal because if we have more fan out, okay, we will have more delay. Okay, fan in is simply the number of input to a gate. Okay, you see this one. How many inputs we have? 1, 2, 3, 4, 5, 6, 7, and 8. So NAND gate with a fan in of 8 is just a simply of number of inputs to a gate. Okay. Now we come to the end, which is the comparison, compare and contrast between these two technologies. Okay, which is the CMOS, the complementary metal oxide semiconductors, and TTL transistor logic. Okay, so CMOS it used FET, which is field effect transistors. You guys can search this from the Google to know about what is field effect transistor, and or the module if there is. Okay, CMOS device is inexpensive. For TTL it is expensive. Okay, oh sorry, TTL used bipolar junction transistor. Okay, for cost wise, TTL is expensive, CMOS is cheaper. And then we have a discharge. Okay, what is the sensitivity for the CMOS? CMOS it is sensitive to electrostatic discharge. Okay, and for TTL it's immune to damage from static electricity. You need to take care of this because if there is electrostatic happen, okay, charge or discharge, okay, it may damage your chip. Okay, so for the CMOS it can tolerate what range of voltage, like just now you guys see, right? It can tolerate from 1.8 volts until 18 volts, so that is very wide. However, for TTL you require well regulated 5 volt power supply. This is normal electronic, normally around 5 volts. Okay, and CMOS it require current that is very low in terms of microampere. However, the TTL is heavy current consumption. For example, can be in milliampere, so it's bigger, right? You can see milli and micro, so it is 1,000 times require current 1,000 times compared to CMOS. Okay, so this is examples of the field effect transistors. Okay, here you have n channel FET, and you have p channel FET. Okay, this is the MOSFET symbol. Okay, the drain gate source. Okay, so this is example of field effect transistor, which is the MOSFET. And BJT, I'm sure you guys learn also from your secondary. Okay, we have collector base emitter. Okay, so this is TTL. Okay, we got TTL where you use BJT, bipolar junction transistor. So with this we finish off the chapter for the logic for that chapter. So please read the chapter 16 in module. Okay, there are a lot of examples for you guys to refer to as well. Okay, please read the slide and please watch my videos, and also please read the module, and please do also exercise with that. Inshallah, I believe you can tackle this chapter very well. Okay, thank you very much and see you soon.